Okay, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1108. If you guys are doing well, let's actually just jump into it. I think, yeah, we just had some examples to do from last time. Let's find them. Da, 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 da. Okay. Okay, here we go. So we have some examples from last time. Really, we're going to work on one today. There are some more. If you scroll down, I'll leave them here for you guys to try. But I really just want to slowly work through one from beginning to end. So you guys can ask me any questions if you want. And just for you to see the process from beginning to end, how it goes from word problem to setting up a linear programming problem to solving it. And then I want to actually talk about why does it work? Because it probably seems kind of weird to some of you that, well, in that whole shaded region, there's like an infinite number of points. How do you know that you could just check these 5 right here, right? It's like, I don't trust you, Jhevon. Like, why? Like, how do you know that the answer isn't somewhere else? So I'll actually talk about that a little bit as well after this example. So going through this example, that's the agenda for today. I'm going to go through this example. We're going to go through it together. I will leave these examples for you guys to do in the notes. And we'll kind of rapid fire, just kill all 3 of them next class. And then next week on Tuesday, we'll start the computer stuff. So if you haven't gotten your Excel and Python in order, try to do that this weekend. And we can, yeah, we'll have fun with that next weekend. But for now, let's actually just jump into this. Nothing new to teach, really. It's just applying what we already know from what we've been doing the past couple classes. So yeah, let's get into it. Here is an example. So animals at a rescue shelter must have at least 30 grams of protein and 20 grams of fat per feeding period. And the shelter has 2 kinds of food to feed the animals, right? So there's food A, which has 2 grams of protein and 4 grams of fat, and it actually costs 18 cents per unit. And food B, which has 6 grams of protein, 2 grams of fat, costs 12 cents per unit. Okay, so food B is bought under contract, maybe some sort of government subsidized contract or whatever, and I have to serve at least 2 units of food B per serving. And another contract is saying that the amount of food B that I serve cannot exceed 3 times the amount of food A. So I'm over here. Okay, so food B, yeah, it's cheaper. I'd give them all food B if I could, if it could meet their requirements. But then it's like, now PETA comes in. You can't give these animals just the cheap food. You have to, you have to balance it out, right? So it's like, okay, no, you can't serve more than 3 times the amount of food A, right? So I have to serve at least 2 units of food B, but it cannot exceed 3 times the amount of food A that I serve. And the question is, how much of each food must be bought to produce the minimum cost per serving? Because I'm running an animal rescue shelter, right? I want to help animals. I don't want to run myself into the ground because I can't pay for everything. So how can I fulfill all my requirements while minimizing the cost that it's going to take? And it turns out, you guys know because we're doing in this section of the class, but if I read this to you outside of this context, would you have noticed that this is actually a linear programming problem? It's a linear programming problem, actually. So that's what this is. This is the situation. So we're going to go through this from beginning to end, kind of show you what you should be doing on like a test and how it's going to go down. So probably part B is not something I would usually ask, but maybe I'll get your thoughts on it next class as well. Interested in seeing what you guys come up with there. So here, let's do that. So like I said, a lot of times with word problems, it's very useful to kind of get away from all the words. So you kind of like put things in a table or something like that. So that's probably what I would do. So let's say here, we know that protein requirements are going to be important. Animals need to get a certain amount of protein. They also need a certain amount of fat. No one cares about how many carbs they're getting. That's fine. It would actually make the problem a lot more complicated. Okay, so there's food A, food B, and the total. So let's say I let X be the number of units of food A per serving. Let Y be the number of units of food B per serving. Okay. All right. So this is the amount of X's that I have. This is the amount of Y's that I have. Now, for A, it has 2 grams of protein, 4 grams of fat, so 2 and 4, and B has 6 and 2. Per serving, I want the total to be at least 30, so there's going to be a 30 down here, at least. And for serving of fat, I want at least 20 at least. Okay. So, yeah, we have that table. This is the food. Right, so that's kind of getting that out of the way, right? So this is the nutrition content. However, we do have other restrictions. Our other constraints are the following. Food B is bought under contract. We need to we need to serve at least 2 units of food B. So this means 1, how much units of Y we serve has to be at least 2. And of course, it's a word problem, so you should know at least means greater than or equal to. Okay. Exceed means greater than, by the way, which means not exceed means less than or equal to. Okay, so it's going to be very important that you know how to interpret these phrases. At least means less, greater than or equal to. At most means less than or equal to. Exceed means strictly greater than. And so to not exceed means you're either less than or equal to. So, okay, so we have those. We also are told that food B cannot exceed 3 times the amount of servings of food A. So whatever I serve for B, it has to be less than or equal to 3 times what is served for A, right? So at least 2 units of B. And here, amount of B cannot be greater than 3 times amount of A. Okay. So, yeah. Also, and this kind of goes without saying, of course, X has to be greater than or equal to 0, Y has to be greater than or equal to 0. Can't buy a negative amount of food. And that's our constraints. So this is kind of how you're starting to set it up in your mind. You don't literally have to write down all of this. I would recommend that you write down the table. But ultimately, what you would do is you would kind of set this up now as a linear programming problem. The LP to solve. Right. So here you're going to want to know what is the objective. What do we want? How much of each food must be bought to produce the minimum cost? We want to minimize cost. So we want to minimize, let's say Z is cost. So what would the cost be here? What is the cost that we want to minimize? So in this example, is anyone there?
Yeah, sorry, what was the question?
What is the cost function with this, in this situation? You want to minimize the cost. What if you pick that out, like how would you describe the cost here?
0.18 x and 0.12 y.
0.18 x and what?
0.12 y.
Yeah, but how do you connect them? What's the mathematical expression?
Are you allowed to combine the two cost programs, or can you only choose one?
You can combine. So that's the idea. You'd buy both, right? Because you have to serve both A and B.
So 0.18 x plus 0.12 y.
Plus, right. So that's going to be 0.18 x plus 0.12 y, right? Because you're buying units of x and y, right? But the cost is going to be that. Notice that that's a linear function. And we have subject to some constraints. So one constraint we can see from the table. If I look in the protein column, it gives me the constraint on protein. So that's 2x plus 6y must be at least 30. So here I have 2x plus 6y must be at least 30. And this is the protein requirements. Looking in the fat column, 4x plus 2y two and 6 together. Yes. 4x plus 2y is at least 20. These are the fat requirements. What else? Oh, we already found here y was greater than or equal to 2. This is contract for B. And we are also told of y is less than 3x. This is requirement for food A. And then we have x greater than or equal to 0, y greater than or equal to 0. These are called the non-negativity requirements. So you're always going to kind of be looking if these guys are an option, right? In this case, if X and Y represents the amount of food you're buying, it really can't be negative. So you have these guys for free almost, right? So there are a bunch of constraints here. Like in a test, I would give you 2 or 3. But here we have like 4 plus the non-negativity requirements. So yeah. So now that's the actual linear programming problem. So it turns out that the problem the owner of this rescue center has is a linear programming problem. Who would have thought? Okay, of course we thought that because we're in the class and that's what we're working on now. But yeah. So now remember how to solve these. 1, you are going to find the feasible region. So this means you're going to sketch the constraints. So we're going to go in. We're going to sketch up these constraints. So we have 2x plus 6y equals 30, which means if I plug in y equals 0, my x would be 15. If I plug in x equals 0, my y would be 5. So this here is 15. This here is 5. And this is the 2x plus 6y equals 30. Go with the next one. 4x plus 2y equals 20. So if I plug in y equals 0, my x is 5. Plug in x equals 0, my y is 10. Four x plus 2y equals 20. Now, I kind of want to know what level this is at. What is that y coordinate here? Because I know I'm going to want to sketch y equals 2, but I don't know if it's going to be above or below that point. So step 2 is to find the corner points, but it's to my benefit to start finding some of them now. So let's first start by intersecting the red and the blue. Okay, someone's trying to get back in here. Okay, so we're intersecting the red and the blue. So this is equation 1, that's equation 2. Let's say I took equation 1 multiplied by -2, call that equation 3. So this is going to be -4x, -12y, -60. Then I'm going to add equations. I'm going to add equations 2 and 3. So that would give me -10y equals -40, or my y would be 4. So I know it's actually going to be below that intersection. This means that this is 4, which means that my y equals 2 is actually going to be underneath this. But let's actually just keep finding the x. This means that 2x plus, if my y is 4, 6 times 4 is 24, equals 30. So that's 2x is equal to, move that over, you get 6, x equals 3. So this point here, let me put that in red, is 3, 4. Right? So we have that. Okay, now what is the other requirement? So I already sketched 3. The last one, y is less than or equal to 3x. So I know that that's going to be a line going through the origin. But you see, it's hard to actually know at this point where it's going to go. Is it going to go like that, or maybe like that, or maybe like that, right? Where it's intersecting is going to be interesting to know. So probably I can see where it's going to intersect on one of these other lines. So maybe intersect it with, say, the red or something. 2x plus 6y equals 30. Intersect that with y equals 3x, which means I can just take this and plug it in here. So now I would get 2x plus 3 6 is 18x equals 30, which means that I have 20x equals 30. So x equals 3 over 2. This means 3 plus 6y equals 30, which means that 6y equals 27. So my y equals 27 over 6, which is 4 point something, which means it's actually going to be a little bit above where the 4 hits. So it's going to hit above like so. So let's actually put that in. What color do I want to use here? Green. So it's going to go through the origin, but hit the red line like that. That should go through the origin. Okay, this one is my y equals 3x. All right. So I've sketched all the constraints. Now let's find the feasible region. What do we want? First constraint, we need to be greater than or equal to 30. If I solve for y, then it's y bigger than that. So for that line, I need to be above. I need to be bigger than this guy. Okay, what else? 4x plus 2y greater than or equal to 20. Solve for y, it's going to be greater than, so I want to be above that line. So for the blue, I want to be above that. Y greater than or equal to 2, which means I want to be above this as well. So I need to be above the pink line. And my y is less than 3x, which means I want to be below the green line. Which means the area that fits all of that is going to be like this area right here. It's unbounded, clearly. All right, so now let's see. I need all my corner points, which means I need to find this guy and this guy. Okay, so I need to intersect the pink and the red. Y equals 2 intersected with 2x plus 6y equals 30. Of course, I can take my y equals 2 and just plug it in here. I would get my 2x is equal, we get 2x plus 12 equals 30, which means that 2x would be, is that 18? X would be 9. So this means you get 9 comma 2. And I also want to intersect the green and the blue, it looks like. So this part I found, I did this part to figure out where to draw, figure out where to draw the the y equals 3x line. And these guys are the needed corner points. Well, I haven't completely found that yet, so let's actually find that. So again, I could plug in the y here. That would mean that 4x plus 6x equals 20. 10x equals 20, that means x equals 2. This means your y equals 6. So you have 2 comma 6. So these guys here are the needed corner points. Those 3. So 2 comma 6 is the other one, so I can write that in. 2 comma 6. All right, so we've found the feasible region and we found the corner points, which is the step 2. The next thing we're going to do is 3, test in the objective function. So notice we've been ignoring the objective function the whole time. The objective function only comes into play at this point, where I know what x values are the ones that I want to consider and what y values are the ones that I want to consider. And I know that this is that. And we have, looks like 3 people. 2, 6, 3, 4, 9, 2. Okay. So the fourth thing is you're finally going to state the answer. All right, but for that, I'll have you guys calculate this. So what are the numbers that we're getting here? Because I don't have a calculator and it's annoying to do on my phone. So
Wait, so just to clarify, are the numbers in the table intersection points that we just figured out?
yes.
Okay.
So once you figured out the feasible region, which is the shaded region, remember you look along the edges of that and you want to find all the corner points, the intersection points.
Okay, thank you.
Right, so in this case, there were 3 of them. Right. So I think we found this point over here as well, but we actually don't need to consider that because it's not on the boundary of the shaded region. We found that in order to know where to graph this. So that's where this part comes in, the x equals 3 over 2 and the y equals 27 over 6. We found that to help us with the graph, but we didn't actually need to. Yeah. So ultimately, we only have to test these 3 points. So what you're going to do is now you're going to just plug in those x and y values into these guys and let me know what you get. So what's the first one?
I got 1.08.
1.08. Okay. Second one, 3, 4.
The second one I got 1.02.
Okay. And the 9, 2.
1.86.
1.86. Okay, so hopefully everyone agrees on that, because it seems like this is the one we want, right? So remember, our goal was to minimize. So we want the minimum one. So here is where we had the minimum z value. So that's the one we want. So the optimal serving costs $1.02 and consists of 3 units of A and 4 units of B. That satisfies all requirements and keeps costs at a minimum. So that is the solution to the problem. If you were the owner of this shelter and you had all these requirements and these were your food choices, and you want to minimize cost, that is the best option. That's what you would do. You do it proportionately. You'd like, for every 3 units of A you buy 4 units of B, and you mix them in those proportions. The animals will get enough protein and fat that they want, carbohydrates be damned, and you'll fulfill all the contracts that you're obligated to, right? Which is interesting that we could actually figure that out. So it was a linear programming problem, and that is the best one. Now, probably want to just spend a few more minutes to actually talk about why is that? Like, why would this even work? I mean, there's so many points in here, right? Like, why is it that I can ignore all points, right? There's literally an infinite number of points in the shaded region and on this boundary. Why is it that I can ignore all the points except the corner ones, right? That's it's kind of sketchy, Jhevon. I don't know if I trust you on that. So I'm not going to prove it in general for you, but I just wanted to kind of give you some idea of why this process actually works. Right? Why would that even be a thing? Like, how do you know you can literally ignore an infinite number of possibilities and focus on these few? Well, here's an hopefully illustrative example. It's not a math class. I'm not going to prove it in general. I'm going to give you an example, and hopefully you can kind of see intuitively why. Oh, I see why we do this now. Suppose the objective was, I feel like you should use were here. I'm not an English teacher, I don't care. Was z equals x plus y, right? So let's pretend I'm giving you a new objective function. What are some values z can take on, right? So you just kind of think, what are the outputs here? So you could have, for example, z equals 1 is a possibility, in which case you get x plus y equals 1, or you can have z equals 3, which means that x plus y equals 3, or you can have z equals minus 5, in which case x plus y equals minus 5. You can get z equals 0, in which case x plus y equals 0, and etc. Right? So you have an infinite number of points you can actually plug in, and you will get these guys here, right? And you guys, but what are these? They're lines, actually. In fact, and they're all parallel. So each time your objective realizes a value, how you can interpret that value is that it creates a line in 2D space, right? So sketching these, you'd realize that you end up in a situation where you're like, a bunch of these lines. Right? So this one is for like z equals 0, z equals 1, z equals 2, z equals 3, z equals 4, etc. And then you have like z equals minus 1, z equals minus 2. Right? They don't have to be integers, but I'm just kind of showing you. Right? Every time z realizes a value, boom, it puts a line where like the y-intercept, in this case, because I gave you a very nice x plus y, the y-intercept is always going to be the z value in this case. But it puts you in this kind of situation where you can tile the entire 2D plane in a bunch of these lines. Now, imagine if there was a feasible region in this situation. So again, so let's pretend we're in the situation where now, so we know that there are a bunch of z's, a bunch of objective lines doing their thing. Right? They're just hanging out. But now someone says, all right, I have a feasible region in here. And so now you ask, well, where is going to be the best z value? Well, you'll notice that as I move up with these blue lines, as I take the higher y-intercept, I get a bigger z value. I start to increase the z value. So it's like, if I had a line that cuts through the middle, let's say I have this line, and I actually want to maximize z, then it turns out I can get a bigger z output by jumping to this line up here. And then still I can get a bigger, so I can keep jumping to these different z lines to keep increasing my z value. And I can keep doing this until this point right here when I hit the edge. See, the moment I pass this blue line, I'm no longer in my feasible region, and I'm just, that's not a solution anymore. However, until that point, I can keep jumping to a different blue line, and I can keep doing this, and I will get bigger and bigger z values until I get to the edge. So you'll notice here that the max z value would occur here. On the boundary. By a similar vein, you will notice that if I wanted to minimize z, get the smallest output of the y-intercept, the minimum value would be here. And again, on the boundary. So it turns out, like if you have a bunch of lines connecting things and you wanted to get like a minimum value, the actual intersection, the corner, the sharp edge is actually going to be the part that's most to the extreme, unless it's actually parallel, right? So you get that. So the corner points are the best place to check. And then if our feasible region had an edge parallel to our objective line, then that entire edge would give a solution.
Wait, in this example, which one's the objective line?
The blue lines.
Oh,
Right?
all of them?
These are the Z lines. Yeah.
Okay.
So the thing is, when you just start the problem, you don't know which the best one is, right? So I just drew a bunch of them, and I'm going to pick the best one after the fact, right?
Got it.
Clearly, by looking at my picture, I see that the best one to pick is going to be one on the edge. It's never going to be one in the middle. Because if I pick one in the middle, I can either move up or down and get a better line, right? I can make the Z value bigger or smaller by moving up or down once I'm in the middle, right? And I can keep doing this until I get to the edge, right? And then sometimes I mentioned that an entire edge would be optimal. And that occurs if something like you had your objective value, and then your feasible region had a line in it that's parallel to that. So then if you have a bunch of things like this, then literally every point along this edge right here is going to be a solution. It will have the smallest Z value, right? Which means if you try this corner, you will get the best value. And if you try this corner, you would also get the best value. But the fact that you got the best value in two corners tells you that the entire line connecting both corners has to also be a solution, because your corners are going to be on the edges of lines because they're linear inequalities, right? So in this case, the entire edge would give me the best value, right? So that's how you can get that's how when you have two corner points giving you the same value, you realize, oh, they both must be the best value, right? So if they're both the max or they're both the min. So you can say, oh, they both must be the best value that we want. But the point is, the answer is always on the edge. It's right outside your comfort zone. Either way, the best answer is always on the edge. And you can notice, if we go back to this example that we were working on, if I were to sketch our objective function, where is it? This guy, he also would look like this kind of line, right? Because your x and y intercepts would both be positive, so it's going to be slanting that way. And if you think of it that way, you realize that really in the background, there are a bunch of objective lines like that. And you know, hey, look at that. The 3,4 is going to be the one that's the most downward. It's going to be the most extreme point that's down here. That's where my Z value is going to be the minimum, right? So, yeah. So you can even tell from if you were to draw a bunch of objective lines, you could tell just from the picture, you would, with no calculations, exactly where the best thing would be. And this is the idea. This is the idea behind that, right? To maximize or minimize the Z value, you keep pushing to the edges. It's always going to be on an edge. Chances are it's going to be on a corner point. If it's not at a corner point, then it means that there are 2 or more corner points that would give the solution. And in that case, every point along the line connecting them is also going to be on the solution, because they'll all be points that fall along the best Z line. So that's kind of why that's why this works out. That's why I know of all the points I could test on this, only 3 of them really matter. Only the 3 that are at the extreme points on the edge. And so that's why we know we can just check corner points to solve these problems. Yeah, very interesting. Anyway, try these for next time. I'm gonna ask you guys what you got, as well as think about the answer to example 1, part B. You're definitely going to want to practice these, because these are going to be, in this class, these are probably some of the hardest ones in terms of how much time they would take to do and blah, blah, blah. So you definitely want to do a lot of practice on these. And you definitely want to get to a point where you can do one of these in like 15-ish minutes or so, you know, when you're rushing. Think about answer to part B in above example. Yeah. So next time we're going to rapid fire kill all these, and then we will do our computer stuff on Tuesday. So hopefully that was understandable. Seems okay. Might leave this up a little bit if you want to take a screenshot, but I'll put it in the notes as well. So yeah, that's pretty much it. Hopefully you guys got that. I'll let you guys go. Have a good rest of your day. Have a good rest of your week. I will see you guys on Friday. See you in the next one. Ciao.